Okay, guys, welcome. Today we're going to talk about sets. Now, first, we'll start with the definition of sets, and that's that if you have any collection of distinct objects, which we call elements, we refer to them as a set. We refer to the collection itself as a set. Now, as an example, we can say that a set would be a deck of cards and that the elements would be the individual cards themselves, right? Or as another example, we could say that a set would be the colleges in Philadelphia, and then the individual elements would be LaSalle, Temple, UPenn, St. Joe's, and of course Drexel, right? Now, most of the time we'll denote a set with a capital letter and list its elements in a set of curly brackets. So something like this, right? So here we have the capital letter A denoting this set, and then we're just listing the colors red, orange, yellow, green, blue, and purple, where A is the set of colors on a rainbow. Now, in mathematics, there are various sets of numbers that are important, right? Now, many times it's convenient to use set builder notation to describe a set with certain properties. And if you're not familiar, we'll sort of discuss that with a few examples. And if it's inconvenient to use set builder notation, what we usually do is we'll list some elements, and then once the pattern is clear, we'll use an ellipses to indicate that the pattern continues forever, right? So of course, a lot of these sets you've probably have seen before, but the first one, of course, is the set of real numbers, which we denote by a capital letter R with sort of that double bar on the left vertical part right here. And then, for X being a real number, most of the time we just use that symbol to denote that X belongs to the set of real numbers. Now, the next one is the set of integers, which we denote by a sort of a capital Z with sort of the double bar there again. And again, that's the set of all integers, so you can think of it as positive and negative whole numbers in addition to 0, right? So when we list that here, it's a little bit more difficult to list in set builder notation without being too descriptive about it. So we can say something like 0, 1, -1, 2, -2, and then the dot, dot, dot would indicate that that pattern goes on forever. And of course, the next elements would be 3, -3, 4, -4, and so on and so forth. And then the next one would be Q for the set of all rational numbers. And of course, this one is helpful to use set builder notation because we can think of our elements as being some P over Q, where those P and Q elements are integers, and of course the number in the bottom is not 0, right? Now, just a comment on set builder notation, we usually started, of course, with the curly brackets and then X, and then either a colon or a vertical bar is used to mean such that, and then in the later part, we just describe properties about X. Right, so those are sort of what we mean by the set builder notation. Now, the next group of numbers is what's called the natural numbers, or sometimes we just refer to it as Z plus, and those are the set of positive integers, or we refer to it as the set of natural numbers. And of course, those are just any numbers that you would use to count. For example, 1, 2, 3, 4, so on and so forth. So it's just the positive integers. Now, there is a little bit of ambiguity about whether the natural numbers include 0. I was always taught that the natural numbers do not include 0, so I will maintain that sort of, I'll maintain that stance throughout the course. So when I say natural numbers, I just mean the positive integers. And now another set that's important is the null set or the empty set, and that's just the set that has no elements. Now, it might seem silly to spend time defining the empty set, but it turns out that it has a lot of nice properties, and it makes the completion of certain proofs much more simple, right? So we can either use the symbol for the empty set, which is sort of this circle with a line through it, Or if we wanted to sort of list explicitly in set form, we could just have two curly brackets with nothing inside of them. Now, another notational thing is that if we have that A is a set and B is an element of our set A, then we say that B and then this funny Greek letter here, and then an A. And of course, this is just the epsilon. And really, when you see this, you can think is an element of or belongs to. All right, so that's just sort of a notational thing. So if you see that epsilon, that just means that B is an element of that set that comes next, that set A. Now, the next concept that we'll talk about in regards to sets is the idea of cardinality. Now, the number of elements of a set A is what we call the cardinality of A, right? And we usually denote that by sort of like the absolute value symbol around our set, right? So you can think of it, it's like absolute value of A, but when we have a set on the inside of those absolute value signs, we just mean how many elements there are. So for example, if we let capital P be the set A, B, C, D, E, and F, then the cardinality of P would be 6. Of course, the cardinality of the empty set would be 0 because there are no elements in the empty set. And the size of the real numbers, the natural numbers, and the integers is all equal to infinity. Now, I should really put an asterisk here because there are different types of infinity. And it is true that the natural numbers and the integers have the same type of infinity, but the real numbers are slightly different. And we'll get into that a little bit later, but for now we can just consider them that they have infinite cardinality. Okay, now the next concept related to sets is the idea of subsets. Now we say that a set A is called a subset of B if every element of A is also a subset, I should say also an element, this little typo, is also an element of B, right? And of course we denote this by A and then sort of a C with a line under it. And you can almost sort of think of these as being analogous to the less than or equal to or the less than symbol. If we don't include the line under it, we use that to indicate that A is not equal to B, because you can have subset inclusion with the sets being equal, but if we don't indicate the line there, we usually use that just to say that A is not B itself, right? And sometimes we call this a proper subset, right? Which just means that every element of A is also an element of B, but it's not that the two sets are not equal. And of course, another way that we can say this is that A consists of certain elements of B. Now, the extreme cases of subset inclusion are if A contains all the elements of B, and that in which case the two sets, of course, are equal, and that's what we just sort of talked about above. Or we could say that A contains no elements at all, and then A would, of course, be a subset of B, right? And that, of course, brings us to the fact that the empty set is a subset of every set, right? So that's one key fact here that we'll always have, is that whenever you have a set, regardless of what's in it, even if it is the empty set itself, the empty set is always a subset of every set. So that's something to keep in mind. Now, among our sets of numbers here, just something to keep in mind, the empty set, of course, is contained in the natural numbers. Now, the natural numbers is the same thing as the positive integers, but we could say that they're subsets, right? And in fact, I would need to make sure that I use the equal there. Now, of course, the positive integers are a subset of all of the integers, which is a subset of all the rational numbers, which is a subset of all the real numbers, which is a subset of one thing we didn't mention, the complex numbers, but we won't really talk too much about them in this course. Okay, so those are just some notes to make about the subset inclusion of some of our sets of numbers. Okay, now we need to talk about some set operations. Now, of course, in all of these, we'll be considering two sets A and B. Now, the first one that we're going to talk about is where we have A and then sort of an upside down U and then B. And we use that to form the intersection. Now, the intersection of two sets A and B is the set that consists of elements that belong to both A and B. So for example, if we let A be the set of all the odd numbers from 1 to 9, and we let B just be 1, 5, and 10, well, then the intersection of those two are what they have in common. So they both have a 1, and they both have a 5, and that's it. So that's their intersection. Okay. Now, if two sets have no elements in common, then their intersection is the empty set, and we usually refer to those two types of sets as disjoint, right? So two sets have nothing in common, we refer to them as disjoint. Now, the next type of set operation that we'll talk about is sort of the opposite of the intersection, and here we use the regular U, and this is used to represent the union, right? So this is, if you have the union of A and B, that would be the set that consists of elements belonging to either one or the other, right? Or both, we should also say, or both. All right, so this is sort of an inclusive union. Now, for example, if A is 1, 3, and 5, and B is 1, 2, and 4, then their union would, of course, be any element that you see. So we have 1, we have 2, we have 3, we have 4, we have 5, and the one that I didn't circle would be a repeat. So I don't need to list it twice, but the union would be all those elements. Now the next one is the difference of two sets. Now the difference of two sets A and B is the set of elements that belong to A, but not to B, right? So whichever one is listed first, you would want to keep those elements that, of course, are not also in B, right? So for example, if we have our A and B the same as before, A is 1, 3, 5, and B is 1, 2, 4, then A minus B would be 3, 5, because I have 3, 5 that are in A but not B, but I would need to take the 1 away because that's what's in B. And of course, if I reverse that order, then I would include 2, 4, because that's in B but not in A, but again, we would also lose the 1. Right? So that's one sort of key result here, is that for the set difference, you would, of course, need to notice that the order would matter there, right? Whereas for the union and intersection, the order doesn't matter. Now, the symmetric difference of A and B is the set of elements that belong to exactly one of A and B, right? So it's in A or B, but not both, you could think of. Right? So for example, if our A and B are the same, we have 1, 3, 5 and 1, 2, 4, then the symmetric difference would be all the elements that only appear one time. And of course, that would be 3, 5 and 2, 4. We would lose the 1 because they're in both. So the symmetric difference, denoted sort of by that triangle, would be the elements that belong to exactly one of your two that you started with. Okay. Now, these operations on sets are similar to operations on numbers, right? You can think of union as sort of being like addition. You can think of your intersection as sort of being like multiplication, and your set difference just being like your regular difference, right? Now, since they're sort of similar to our operations on numbers, it makes sense that we should have certain rules and certain identities, right? And the first one that we'll talk about is the following, where for any three sets A, B, and C, we have that A intersect the union of B and C is equal to A intersect B union with the A intersection C. And this is sort of like the distributive property. Because, for example, if you were to think of these as just numbers, then we have A times B plus C would be on the left side. And on the right side, you would have A times B plus A times C, which of course is valid in the real numbers, right? So we sort of see an analog here. Now, how can we prove this? Now, the way that I'm going to prove this is sort of the standard way to prove this, but we'll talk about sort of a nice way that will allow you to visualize this, which should help you, make valid proofs for this as well. Now, what we need to show two things. We need to show that the left side, the left side is a subset of the right side, and also that the right side is a subset of the left side. Now, of course, if you have both of these things, if you have that each one is a subset of the other, that concludes that the things have to be equal, right? Which, of course, is what we're trying to show. So we need to show two things. We're sort of doing two little mini proofs in one here. Now, the way that we do this, we'll start with showing that the left-hand side is a subset of the right-hand side, is we're just going to let an arbitrary element that we'll call x belong to the left side. And then the goal is to show that x also belongs to the right side. Okay, so that's what we ultimately want to show for this first part of the proof. Now, if x is in A intersect B union C, this means that x, then x is in A and, right, because the intersection means and, x is in B or C. Right? And now we sort of have two cases, right? Because we either have that, let's put it this way. Then we have that x is in A and x is in B, or x is in A and x is in C. Right? So we're sort of using the definitions of intersection and union here to write out sort of in words what's happening. Right? And this is sort of flowing by logic so far. Well, now we have exactly what we want to show, right? We have then x is in the intersection of A and B, right? Because that's what this is saying, or x is in the intersection of A and C. Well, then what does this mean? The or means that x is in their union. Right? So now we've showed that our goal, we've shown that x is an element of A intersect B union A intersect C. Now we just need to show the other direction. Let me give myself a little bit more room. Okay. Okay, here we go. Any minute now. Okay. So now we need to show part two. And of course, the argument's essentially going to go the same way that we did before, just now in reverse. Right? So now we're going to let x be an element of A intersect B union A intersect C. And now the goal is to show that x is also in A intersect B union C. Right? So now if x is in A intersect B union A intersect C, then we have then X is in A and X is in B, or X is in A and X is in C. Well, of course, here we see that no matter what, X is in A, right? Now, X is in A and either X is in B or X is in C. And of course, now we're there because this says then X is in A intersect B union C, right? Which of course is what we wanted to show. So 1 and 2 together show that A intersect B union C is equal to A intersect B union A intersect C, right? Which is what we wanted to show. Now, this type of argument is pretty standard for proving your set equalities. However, a lot of times it may not be easy to visualize this, and it can be easy to make a mistake, right? So another way that we can see this is if we use a Venn diagram, right? So if we have 3 sets A, B, and C, then we can form their Venn diagram, and now we have all the possible scenarios here, right? Because, for example, if I wanted, say, A intersect C, that would be this region right here, because that's where A and C overlap, right? If I wanted, for example, A union B, well, A union B is everything that's in A or B, so I'd have this as my A union B, right? And we can do that for any of our different set type of operations here. Now, if we were to look at the left side, which is A intersect B union C, well, we know that B union C would be both of them, B and C shaded together, and then I would need to intersect that section with just what's in A. So that's going to give me sort of these 3 pieces right here. Now, if we look at A intersect B union A intersect C, we see that, well, A intersect B, of course, would be this part, and A intersect C would be this part. And we see that in both diagrams, we have the same regions shaded, right? So since the same regions are shaded, we know that the sets are equal. And that's a nice way to visualize it. And that usually gives you a good intuition of how to go about doing the proof if you're, if you're sort of getting stuck on it. Right, and this is what I said at the beginning, right? That we can think of union being similar to addition and intersection being similar to multiplication. Then you sort of see that you have this similarity to the distributive property. Now, we also have rules for, of course, the commutative property and associative property, which I think are easy to see, right? If you were to look at the commutative properties, that just means that the order doesn't matter when you're looking at set intersection or set union. And for associative, the order in which you do these things doesn't matter as well. All right, now the proofs of these are very simple, and if you wish, you can try them on your own, although there's not much to them. All right, so let's do another example where we have a set inclusion proof, okay? Now, this has no analog to the real numbers, right? Because if you were to translate this to the real numbers, you'd have something that's not true, right? So this is sort of a standalone set equality proof, right? Now, we just saw that if I want to show that these 2 things are equal, I need to show that this is a subset of this, and I also need to show that this is a subset of this. So we sort of have to do our 2-in-1 proof here again. Now, let's go ahead and let's look at this in a Venn diagram first, since we just spent some time talking about that. So let's go ahead and we'll just show both the left and the right-hand side on this. Okay. Now, on the left side, we have A union with, right? So I know that I'm going to be taking A no matter what. And I want to union that with B intersects C. And of course, B intersects C would be this part right here. Right? Because that's the region where both B and C overlap. Now, if we look at the right side, let's see what we have. So we have A, B, and C. Now I want to take A union with B, and I'm intersecting that with A union with C, right? Well, now both of these both contain A, right? So A union B, of course, would be B and A union together, right? So it would be all of this stuff, right? And I want to intersect that with A union C, which would be all this stuff. And now, of course, where I want to have the actual diagram here is the stuff where they overlap, right? Because I'm looking for the intersection. Well, of course, that would be the same thing. That would be this middle part, and that would be all of A, right? So we see that these things should be equal. So let's go ahead and let's try and do it with a proof. So let me just rewrite this down here so I don't have to keep coming back and forth. Okay. So let me give myself a little bit more room. Okay. So first, let's show that A union B intersects C is a subset of our right side. A union B intersect A union C. So of course, how do we start this? We let X be an element of the left side. So X is an element of A union B intersect C. Well, what does this mean? Then this means then X is in A or X is in B and X is in C. Okay. Now here it may not be clear as to where we go from here. And what we can do in that case is let's go ahead and leave ourselves a little bit of room. And let's try looking at the other direction. Let's try looking at A union B intersect A union C and proving that that's a subset of A union B intersect C. And a lot of times this will give us some insight on what we can do in the other case as well. So let's let X be an element of the left side. A union B intersect A union C. Well, what does this mean? Well, this means then X is in A or X is in B and X is in A or X is in C. Right? So it looks like we're either going to have here then, we're either going to get then X is in A, right? Because we have X is in A or X is in B, and X is in A or X is in C. So let's suppose here that we have our X's in A. So I really should say if here. So if X is in A, then it may or may not be in B, right? But we're definitely going to have and X is in A or X is in C, right? So let me give myself a little bit more room. Okay, now if we look at the other scenario, if X is in B, then X is in A or X is in C. So what it looks like we now have is that if X is in A, well, then X is in A. But we could also have or X is in B and X is in C. Right? And this, of course, is what we want to show. Then this means then, I should say then. Okay, so then X is in A union B intersects C, which of course is what we wanted to show. Right, so now we can use this part of the proof to give us a little bit of insight on the previous part that we wanted to show. Okay, so now if X is in A, then X is in A, right? Right, if X is not in A, then X is in B and X is in C. Right? So it looks like what we have here is that, oops, not, I should say then. Then we either have X is in A or X is in B and X is in A or X is in C. Right? And this would cover all of our cases. So then we have then X is in A union B intersect with X is in A union C. Okay, so if now we've shown both sets of inclusion, so of course 1 and 2 together show our claim. And of course, this proof was a little bit weirder to do, right? We have some weirder stuff going on, but it was nice to do the Venn diagram before in order to convince ourselves that these definitely are equal, right? So then from there, it's just a matter of sort of finagling the logic to make this thing work. All right, so that concludes this video on an introduction to sets. I hope you enjoyed, and I'll see you next time.